Good afternoon, everybody. My name is David Pugh. I am a staff scientist at the CALS Visualization Core Laboratory, and this afternoon we're going to be covering an introduction to Conda for data scientists. This workshop is a part of the Introduction to Data Science workshop series that KVL has been running for 2 years now here at CALS. The goal of this workshop series is to try to build capacity in the foundational tools for doing data science and machine learning, particularly Python, Shell, Git, SQL, Conda, package environment management with Conda. These capacity building trainings are part of a broader effort here at the university to develop and promote progress and research in machine learning, data science, artificial intelligence, and things like that. Today, I'm really happy to be using compute resources, a binder hub provided by the CALS Research Computing part of IT. So my colleagues over there are the ones that have provisioned and provided the computing resources that we'll be using today for this training. And for those who are joining from off campus, we're using Binder Hub, but the public version of Binder Hub provided by the MyBinder team. And I'm very grateful. I've been using the resources for several years now for trainings and workshops and courses like this. And it's just a fantastic project. So as always, thanks to them for providing the awesome free compute. Okay. So let's go ahead and take a look at what we're going to cover today. So today we're going to do an introduction to Conda for data scientists. So Conda is an open source tool that solves two really important problems that data scientists face. Managing software and all of the dependencies of that software that you need for your projects, and then also keeping your different projects isolated from one another in different kind of environments. And that way, those are two related and two important problems that data scientists need to solve. Not just data scientists, but really kind of anybody doing computational science is going to run into the same two problems. And as we're going to see, Conda is a great tool for solving both of those problems. So roughly speaking, I've broken up today's training into 5 episodes. So the first episode is on getting started with Conda. This is just going to be the complete basics. What is Conda? Why should you use it? What is the package and environment management system? Things like this. And then the second and the third episodes are kind of, I would say, 2/3 of the core content of the training. So in the working with environments, we're going to cover all of the basic commands for using Conda to create a virtual environment. How to create, delete environments, activate and deactivate them, installing packages, updating environments, figuring out what's already installed in environments, figuring out what environments you already have on your machine, these kinds of things. And then sharing environments, where we're going to see how we can specify a Conda environment.yaml file, which is a structured text file that will describe the contents of your environment. And then you can share this environment file with your colleagues or your research peers. You can make it available on GitHub or GitLab, and it makes it easy for others to reproduce your software stack on their machine, or for you to port your software stack from your local machine or workstation to a remote computing cluster like Ibex or public cloud, or possibly even Shaheen as well. Then the last episode that we will probably cover in detail will be managing GPU dependencies. So we'll quickly go through packages and channels. That's episode 4, but we'll move quickly to managing GPU dependencies. And so because we have such fantastic GPU computing resources here at CALS, and our data science machine learning research is growing, there's a lot of demand for the Nvidia GPUs that we have available here at KAUST. And Conda is a great tool for managing the additional software complexity that comes from working with GPU accelerated data science machine learning libraries. So that's kind of a rough sketch for the day. So any questions before we get started? You can either ask them in chat or you can unmute yourself and ask questions. No? Okay. Well, then let's go ahead and get started with Conda. Okay. So in this episode, there are three kind of key questions that we want to answer. The first is just, what is Conda? The second is, why should you use a package environment management system as part of your research workflow? And so for that question, I'm really going to try to hammer home the benefits of using tools like Conda to manage your project environment separately and to manage the software stacks within those individual projects. And then we're going to talk about in particular, why Conda, and then I've put plus pip down there in parentheses, and we'll talk about what I mean by that, as opposed to some other tool. Okay. So here we go. So Conda is an open source package and environment management system. So it runs across major OSs. So Windows, Mac, various flavors of Linux can all run Conda. So it can install, run, update packages and their dependencies. So that's Conda being used as a package management tool. So anybody who has used Python or R or JavaScript or any kind of programming language, there's usually not just like the core programming language. There's also all these other libraries that have been created by the community of users of that programming language, and you often want to install some of those libraries for use in your projects. You might need to have different versions of those libraries. So Conda is a tool that can do that, not only for Python, but as we're going to see, also for R, Java, JavaScript, a whole bunch of other languages, Fortran, C, C++. Now, Conda not only installs packages, but also allows you to create separate environments in which to install those packages. So you can have a different environment for each of your projects, and then potentially have different versions of the same packages installed in those separate environments. This is really handy so that you can have, you have maybe an older research project that needs older versions of software, and then you can have an environment that has these older versions, and you can then switch to other projects with newer versions without breaking your code that worked in this older on this older project. So that's really important. And that's kind of Conda is both a package manager in that it helps you find and install packages, but it's also an environment manager in that it helps you have these different environments where you can install either different packages in those environments or different versions of the same package in those different environments. Okay, so that's the answer to what is Conda. Just to try to clear up some confusion, so there's Conda, the package and environment management tool. That's this here. But Conda is distributed via two different mechanisms. One is Miniconda. Now, Miniconda is the version of, or the distribution of Conda that I encourage you to install, and that either on your local workstation or your laptop, or on Ibex or Shaheen. And that includes the Conda tool plus its own version of Python plus some operating system specific packages. So, operating systems, in order for Conda to install packages, it has to interact with your operating system. And depending on what operating system you're using, those interactions take different forms. And so you need different packages to go along with the base Python that is different from your system Python. So Conda will never use your system Python to do anything. That's very important. And then there's Anaconda, which includes Miniconda, but then plus several hundred at this point additional Python packages, kind of skewed towards data science, machine learning, scientific computing users, as opposed to like web development or other kind of corners of the more general Python ecosystem. You can install either Miniconda or Anaconda. Not both, you kind of pick one or the other. I encourage you to go with Miniconda. It's a little bit lighter weight. It'll encourage you to use Conda in kind of what I would say is the best practices way of managing your software stacks, and kind of discourage you from some ways of using Conda that might seem simpler to get started, but actually slow you down in the longer run. Okay. So now I want to kind of motivate just briefly kind of the ideas behind package environment management system, why you would want to use a tool like Conda, things like this. But before I get into that, just to make sure we don't lose our compute, I'm going to go back to my Jupyter Lab, and I'm just going to open a terminal window. And that's it. We'll come back to using that terminal window in a little bit, but just to make sure that we haven't lost or hasn't timed out on us, I wanted to go ahead and check on it. Okay, so why should you use a package and environment management system? Why shouldn't you just, if you need some software, why don't you just install it? You need some other software, then why don't you just install that software? Why should you have another tool to manage this process for you? The reason is that, if only it was that easy, right? So installing software is hard. And installing scientific software is generally even more challenging for various reasons. Probably the most, the reason that I encounter the most is that most scientific software is not necessarily written to be easy to use by other people. It's written by a particular scientist to get their work done, to get their research done. And then once their research is done, they might chuck the code up on GitHub and make it available, but like it may not necessarily ever have really been meant to be used by someone other than themselves. So it can often be really challenging. So because it's so challenging, historically, the typical approach has been to just install software once, system-wide, and then just install more software on your system. But this kind of approach, just installing everything on your computer without isolating them from the rest of your operating system and from the different projects themselves, has a number of problems. So the first is that it becomes very difficult to figure out what software is actually required for your research project. So if you're just installing stuff on your laptop and somebody says, well, geez, David, what software are you using? How can I reproduce your work on my machine? If I wasn't using a tool like Conda, I might say, well, okay, I have some rough recollection of the software that I installed. So here's the software that I installed. And they might install it and then come back and say, oh, it's not working. So what else is there? Well, maybe there's these system dependencies, and then you start digging, and eventually you more or less come back with, well, it works on my machine, and that's kind of all you can say. And tools like Conda are going to help us do better than that. Okay, so the second is that when you install things system-wide, it's basically impossible to have different versions of the same software installed at the same time. And this means that, if you had your research project from, say, your master's or the first year of your PhD, and you had all your software installed and everything worked fine, and then you came back to start the next year and you're working on a new project, and now you need more recent versions of the same software. So you install these more recent versions, and then all of a sudden you go back to check on something with your old research project and it doesn't work anymore because there was something in your old research project that requires older dependencies of the software that you updated. So then you have to maybe manually revert to go back and work on your old research project. And then when you come back to your new one, you've got to upgrade again. this manual process of going back and forward is really tedious and error prone and just waste a huge amount of time. Like, that's not what you want to be doing as a research scientist. So Conda is going to help us solve that problem as well. And the way that we're going to solve this problem is actually moving away from system-wide software installs and towards a workflow where each individual project is going to have its own software stack that's installed in its own environment, where we have a single file that explains exactly what's been installed in that environment. And if anyone ever asks, what software do I need to reproduce your project, or what software do I need to start working and contributing, collaborating on your project, all you have to do is give them this environment file and tell them one command, and they can rebuild their software environment, or your software environment on their machine using Conda. So that's what we're going to move towards. Okay. So let's kind of dig a little deeper about the benefits of environment management and package management. So these are two problems, but they're very much kind of related or complementary to one another. So with environment management, the environment management system solves kind of a very important problem. So the first thing it solves is that it isolates your different project software requirements from one another. And this immediately allows you to install different versions of the same software on your computer at the same time. You just install them in these different environments. And it helps make your projects more reproducible, because again, it will capture the software dependencies in a single file. It also makes your projects more portable, so you can move them from your laptop or your workstation to computing clusters like IBEX or Shaheen here at KAUST, or public clouds like AWS, Google, or Microsoft Azure. And in the instance of Conda, it allows you to install packages on systems where you might not have admin privileges. So not everyone has admin privileges on your university laptop. You can sometimes ask IT and get admin permissions for your laptop, your workstation, but you might not be given them automatically. And certainly you will not have admin privileges for most remote computing clusters on which you will work. So in that case, you need a mechanism to install software that doesn't require admin privileges. And by installing software into these virtual environments, instead of installing them in locations where system software is installed, you can install software without having this kind of special admin privileges. Okay. So any questions about environment management? Kind of what it is, why it would be useful? No? Okay. Okay, so there's environment management. Environment management is all about isolating project software stacks. Package management, so once you've accomplished the isolation, once you've solved that problem, you still have the problem of, okay, well, now I need to install software, and I have some key software that I want to install, but then I also have dependencies of the software that needs to be installed, and I need to do this for every one of my projects. So if I'm going to isolate my software environments for my individual projects, then I definitely need a good package manager in order to install into these different environments. And the concept of package management, so if you're using Linux, then you've been using package managers from day one, because Linux has built-in package managers for their operating systems. They have different names depending on what flavor of Linux you're using. If it's Ubuntu, it will be apt. If it's CentOS or CentOS, it will be Yum. Mac has something similar called Homebrew Project, which ports kind of a Linux-like package management system to Mac OS. or Mac OS. Windows, up until recently, I didn't think Windows had a package manager, but there's the Chocolatey project, and then actually I think Microsoft is now developing for newer versions of Windows 10 and later, is starting to develop its own kind of Windows-specific package management system for installing things. So those operating system package managers give you the basic idea of what a package management system, the problem that a package management system needs to solve. Our problem is actually simpler in that we don't necessarily need to install, operating system low-level software so much. We just need to manage our software stack for usually a core scripting language like Python, R, and SQL, and then maybe if you're doing like data science and scientific computing use cases, then a lot of this software is going to wrap C, C++, Fortran, low-level binaries, and so we need a way to install dependencies for those as well. And so those are kind of the problems that we need to solve. Okay, any questions about package management? No, okay. So to wrap this up, I just want to wrap up this kind of motivational episode, I just want to talk about, so why should you use Conda and pip for this? So there are many different kind of package environment management systems. Most of them focus on either the environment management problem or the package management problem. So you would have to use one tool to manage your environments like virtual env or pipenv. And then one tool to manage your package installations like pip. Conda solves both. It is both an environment management, it both manages environments and installs packages. So it's kind of one tool to solve both of these problems, and it solves, I think, both of these problems really well. And it integrates with tools like pip for installing packages that maybe might not be available via Conda. And again, it's cross-platform, so that's really useful, which helps facilitate reproducibility and portability. And it's particularly targeted at data science, machine learning, scientific computing users. So we'll talk later in maybe the packages and channels episode briefly, but Conda distributes precompiled binaries. And what this means is that Conda can distribute binaries compiled to target your hardware on your laptop, your workstation, or IBEX or Shaheen to a lesser extent. And it can do that in a way that allows you to get a lot of these low-level C, C++, Fortran codes that are widely used in data science, machine learning, scientific computing, or GPU-accelerated binaries. These things can be distributed and installed via Conda, and other tools like pip can't do that. They're basically specifically focused at, in pip's case, Python, installing Python packages. So it's kind of an advantage that I think Conda has over pip. So for me, the Conda plus pip in parentheses is to try to capture the idea that I think you should use Conda wherever possible and then install via pip only where necessary. And we're going to see a lot of examples of this through the rest of today. Okay. So that's kind of the intro, just to kind of explain to you, what Conda is, talk about these two problems that Conda is solving, the environment management problem, the package management problem, and kind of place it in a little bit of context so that you have some idea of why you should learn a tool like Conda. So I'm briefly going to stop sharing. And are there any questions now about Conda? Are any of you using Conda now? Are any of you using pip now? So pip is the default kind of built-in with Python package manager. So it's usually the first place that people get started. Okay. Okay, cool. Well, then let's, since there's no questions, there seems to be, people have a little bit of familiarity with Conda and then possibly pip as well, but let's go ahead then and we'll just head on to the next lesson and get started actually using Conda. So at this point, share my screen again. So at this point, I'm going to switch away on the screen sharing from the lecture materials and switch over to the Jupyter Lab. And I'm going to be kind of doing a live demo at this point. I have my lecture notes up on another screen, on my laptop actually. And so I'm going to mostly be doing live demos from this point out. So, and I will occasionally refer back to the lectures. Okay, so just in case you guys missed how I got the terminal. So if you've not used Jupyter Lab before, it's not a big deal. We're not really going to be using Jupyter Lab much today. We're just using it as a mechanism to get access to a terminal, basically. And we're going to be using Conda via the terminal for the rest of the day. So the Jupyter Lab landing page looks like this. You've got your file browser over here, which you can toggle on and off by clicking this folder. So you can go off and on and off and on, off and on. I will mostly just toggle it off so that there's more workspace here. And then if you just click on the terminal, you will get a terminal. And that's pretty much it. So since I'm going to be typing commands, can you read this? So just a quick in participants, if you could just check yes, if you can read. Just want to make sure everybody can read. And then if you want it to be a little bigger, just send something in chat. Let me know that it needs to be a little bigger. And okay, so that looks pretty good. So good, everybody can read this. So yes. Yes, the command cannot be found. Okay, cool. So let's get started. So the first thing that we need to learn how to do is create an environment. Now, whenever you install Conda, Conda has a base environment. And so you can look at what environments are installed by typing the command Conda Conda environment list. And that command basically lists the environments that are currently installed and the path from the root of the file system to the location of the directory containing the Conda environment. So a Conda environment it's just a directory. So when I talk about creating different environments, what I really mean is basically creating a directory and installing a bunch of software into that directory, instead of installing it into system folders where you would install software. So we're just installing it into a directory. And if you install Miniconda locally on your computer, then you will have this base environment here that comes by default. So that includes a new version of Python that's not the version of Python that's already installed on your system. So Conda will come with its own version of Python, and then some operating system specific packages. It's always a best practice to avoid installing software into the base environment. So we're going to be creating additional environments and installing software into those. We're never going to install anything into the base environment. The only time we would ever install something into the base environment is when we update the Conda tool itself. Now you'll see that here on Binder, or on the Binder hub, there is a second environment called Notebook. And this notebook has an asterisk or a star character next to it. So that's because the notebook is the currently active Conda environment. We'll talk about what active and how to activate environments and deactivate environments. But the fact that this notebook environment is the active Conda environment means that if we were to type the which Python command and hit enter, so this is telling us basically where in the file system is the Python binary that you would use if you typed Python and then did some other stuff with Python. So if you look at the path, you'll see that it goes into the notebook environment, into the bin directory within the notebook environment, and then finds Python. So when you type Python, you're getting Python 3.8.6, but that's the Python in the notebook environment. So we're going to be creating our own environments and installing our own versions of Python in those environments. And they'll be different than the Python that is in the notebook environment, which is itself different than the Python that is in the base environment. Or potentially different. It might be the same in this case. So we can type exit to get out of that. Okay. So again, don't install things into the base environment. The only thing you do with the base environment is update Conda if and when you need to. And but we don't need to deal with that at the moment. Okay, so let's create our own environment. So the Conda command has a help menu, and the help menu shows you all the different kind of main Conda commands. So there's a Conda create command, which, as you might expect, creates environments. There's a Conda install command, which installs packages into a particular environment. There's uninstall commands, which is an alias for actually remove. So Conda Remove is what we use to remove packages or an entire environment. So we're going to basically see a lot of these commands in this episode, basically. Not all of them, but most of them. Okay, so I'm going to type. There's a bash command called clear, which just clears out the terminal window so that we have more space. So let's create our first environment. So we're going to do Conda create, and then if we were to run help on Conda create, we can see the help menu for the Conda create command. So at the top, it will tell you kind of, it will give you kind of the syntax for using it, then list and explain all the different options and things like that. In particular, we're going to be creating Conda environments start out by name. So we're going to have to specify either the -- name or -n, and then the name of the environment that we want to create. Later today, we're going to cover what I use as my best practice, which is installing into a particular location by providing the path to the directory I want to install into. But we'll talk about that later. There's some more advanced options here, like using different channels. Maybe talk about that later. Most of these options I don't use on a regular basis, and so don't be overwhelmed by the complexity of this help menu. I just wanted you to know that it's there. Okay. So we're going to clear that out again. Okay. So Conda create by name. So it's always a good idea to give your environment names, something sensible, something that will help you remember what it was supposed to be used for. So if your project has a name, then you could put like the project name -env or something like that. In this case, we're going to create a simple Python 3 environment. So I'll just call this Python 3 environment. And then after the name, now we just do a list of the packages that we want to install into this environment. So we'll start out with something just simple. So Python and pip. So it's always a good practice to install pip into every Conda environment. So the reason for doing this is that it avoids common errors that I see with many users when they are trying to use Conda and pip together to install packages. So most operating systems include Python, and most operating systems actually include pip as well. And that's because the designers of operating system need to install Python packages, and they use pip to do that because pip is the kind of built-in default Python package manager. But that means that if you're not careful, then you might pip install something, think that you're installing it into your Conda environment, but actually installing it into your system directories, which is not what you want. So you avoid this by always installing pip into every Conda environment. That way, whenever you use pip install for something, it will install into your Conda environment as expected. So we're always going to install pip. Okay, and now if you hit enter, Conda will go and look for Python and pip, and it will figure out what are the most recent versions of Python and pip that are mutually compatible with one another. And then it will go and figure out, well, what dependencies does Python and pip have? Find the most recent versions of those dependencies that are consistent with one another. And then go again, what are the dependencies of the dependencies? And so on and so forth until they have no more software to install. And so that's kind of the magic or the complexity that Conda manages for you. So here, if we take a look at the kind of the plan of what Conda is going to do once we say yes, is first off, we get a little warning saying that there's a newer version of Conda. Okay, fine. We can update to a newer version of Conda, and it gives you actually the command to update the base environment and then Conda. So we can actually run this command in a minute and then update Conda. So I'll show you how to do that. Then the package plan. So it tells you where the environment is going to be created. So it's going to create an environment in the default location, which on this version of Linux is in srv conda/envs. And then the name, so you can see the name has been given to the directory that we're going to install into. And then it's the list of the packages that we want to install. And then here you can see the actual versions of the packages that Conda has downloaded, including their build numbers. And we'll talk later about what build numbers are. And then the last column is the Conda channel, where Conda has installed the software from. And we'll talk about what that means a little later on as well. But if you look through here, you'll see here's Python. We asked for Python, so that's 3.9. So we got Python 3.9, which just recently came out maybe about a month ago. And then pip 20.2. And then the rest of these are actually the dependencies of either Python or pip, and then dependencies of those dependencies and so forth. Some of which are operating system specific. So in this case, we're running in the cloud on Linux. So some of these are Linux specific packages. And so if you were to run this environment command on Mac or on Windows, you would have a slightly different list of packages here. You'd still have Python and pip, but you might have a slightly different list of dependencies that are relevant for your operating system. Okay. And now if we type, it says proceed, yes or no. So if we type Y and hit enter, at this point, Conda actually starts downloading these packages. So these packages are actually just tar files, compressed files of precompiled binaries that it's downloading. Conda's downloading these. So you do need an internet connection in order to use Conda. In order to use Conda to create an environment, you need an internet connection because Conda has to download the software from the web. But once you've created an environment locally, then you no longer need an internet connection to actually use the environment. And then at the end, once we've downloaded everything and verified that what we've downloaded is legit from legitimate sources, and then we have created the environment, that's the executing the transaction part, then we have given a hint, here's a command, Conda activate, and the name of your environment that you can use to activate the environment, and then a Conda deactivate command, which is how you would deactivate that environment. Okay, so we'll talk about environment activation and deactivation in a minute. I just wanted to kind of walk you through the process. All right, so we've done it once, so let's do it again. So let's clear. Now let's suppose instead of the most recent version of Python, we wanted an older version of Python. So we can specify a particular version of Python by just saying Python equals, say, 3.6. So that's a very common version of Python that is generally compatible with most packages and things like that. So we use Python 3.6 and pip 20.0 instead of 20.2. And now if we hit enter, so now I've gotten this warning. Because I have not changed the name of the environment, Conda is giving me a warning and saying that this environment already exists. Do you want to remove it and like overwrite it? Yes or no. So I'll type no, and then it will exit. Because what I should do is change the name of the environment. So this is a Python 3.6 environment, so I'll call it Python 3.6. And now if I hit enter, the same process is going to be done again by Conda. Notice that there are fewer packages to download. And that's because Python 3.6 and pip 20.0 have dependencies that are already been downloaded, that are the same dependencies with newer versions of Python. They're also compatible with Python 3.6. So pip doesn't need to, or Conda does not need to download them anymore. There are a few other ones that have to be downloaded and then installed. So we can just hit yes and hit enter. And then off we go. So downloading, verifying, executing, and we're done. Okay, cool. So I tend to always specify the version numbers of packages that I want to install, unless I really am just like prototyping something or playing around with something, or I want to test some software, some example that I found online. I think it's a good practice to get into, because when you specify your version numbers, then you kind of always know exactly what software works. And that's just a good practice to get into. But of course, you might not know what version numbers you are even available, much less the version numbers you want. So there's a handy command, I'm just going to clear this out, called Conda Search. You would have seen it in the help menu, I believe. Yeah, so search. So it's search for packages. So that basically this allows you to, let's do Conda Search help. This allows you to search for packages. And so there's a menu here of different options that you can take a look at. There is some handy kind of wildcard pattern matching. So you can do Conda Search star scikit star, and that will return anything that has scikit in the package name. So we can try that. So if we do Conda Search star scikit star and hit enter, we'll get a bunch of stuff back. That's because scikit is kind of the packages that are designed to be extensions of the SciPy project. packages that are very much related or build upon SciPy, but are not generic enough to warrant inclusion in the SciPy package itself. Will be released under the scikit moniker. And so you can go through here and you can see, well, there's the scikits, ODEs for ordinary differential equations, and UMF pack. I have no idea what that does. Scikit surprise, no idea what that does. The one that we're interested in is scikit. So there's scikit optimize, which is actually a hyperparameter tuning library, or it can be used for that. That is built upon scikit-learn, but what we're interested in is actually scikit-learn, which is the, so let's do scikit-learn. So scikit-learn is the kind of the library for doing, I'll call it classical machine learning, so not deep learning, but other kinds of machine learning libraries in Python. I'll be providing some training on this on Thursday this week and Thursday next week. We'll be covering different parts of scikit-learn. But now we just want to learn how to install it. So if you look through here, you can see that, well, actually, let's not dig through all of this. Let's get rid of the stars and just do scikit-learn. And then we can see what versions of scikit-learn are available. Okay, so the most recent version that's available is 0.23. And then you can see if you scroll up, there's a bunch of older versions going back probably 2 or 3 years. And if you look closely at the build, so the left column is the name of the package. The second column is the version number. The third column is the build number. And if you look at these build numbers, you might see things like, here's Pi 3.6. So that's a build of SciPy or scikit-learn for Python 3.6. This is an older version, 0.18 of scikit-learn. So newer versions of Python were not available at that time. So Pi 3.6 was probably the most recent version of Python available at the time. There's also a Python 2.7 build for that version of scikit-learn. If you kind of scroll down again, eventually these Python 2.7 builds will drop away because most libraries stop supporting Python 2.7 in January of this year. And then eventually you'll see even more recent versions of Python 3.6 probably drop, or Python 3 drop out. So I think scikit-learn probably stopped supporting Python 3.6 relatively recently. Let's see. Oh, no, they still do. So Python 3.6 is the oldest version that, wait, no, we're not even at the most recent version. Sorry, still need to keep going. So Python 3.6, 2.3.2. So here are all of the different builds of scikit-learn 0.23.2 for the different versions of Python. So you can see there's one build for Python 3.9. There are several different builds for Python 3.8, Python 3.7, and Python 3.6. Okay, so that's the Conda Search command. So let's create another environment. So Conda create. Let's do something a bit more realistic. So we will create a basic SciPy environment, and into this environment we will install Python, IPython, Matplotlib, NumPy, pip, and SciPy. And I'll just go ahead and leave the version numbers off just to kind of see what gets picked up. So, and I'll just hit enter at this point. And again, if you don't specify the version numbers, then Conda should find the most recent mutually compatible versions for the libraries that you've asked for. So if we go up here, let's look and see what's been installed. So we have a Python 3.7, NumPy or SciPy 1.5, NumPy 1.19, Matplotlib 3.3. Let's see what else. IPython 5.8. And I think those are the ones that we requested. Okay, so let's just hit yes and hit enter. So now we're going to download all these packages and then we're going to install them. So it's the same routine for the simple environments that we created at the beginning, the Python 3 and the Python 3.6 environment. So now we just have more software, so it might take a little bit longer to install the dependencies and everything. But hopefully not too much longer. And so there we go, done. So another thing that you can do is, well, let's say that you don't really care too much about the version numbers for some of the packages, but you want to make sure that you're using a more recent version of, like a minimal version of Python, for example. So let's say like you really wanted to use Python 3.8 or greater. So then you could put Python greater than or equal to 3.8 and then leave the rest of the version numbers unspecified and basically allow Conda to choose which to install. So now if you hit enter, I'm not quite sure what's going on here. I'm going to hit Control and C on that to slow that down. One thing I did want to do was to come over here and just change the name, Python 3.8. Let's try this again. There we go. Looks like it was just a slow compute instance. Not quite sure why this is taking so long. Is this taking long for everyone else? So can you just respond via chat if you're trying this command and it's just hanging like this for you, or is it working for other people? I'm curious. No responses. Come on, guys. Okay, well, I'm not going to wait for this any longer, so I'm not quite sure why this is being slow, but what this would have done is it would have come back and found a Python that was at least as recent as Python 3.8, and then the most recent set of dependencies for the rest of these that that were compatible with Python 3.8. Okay, so now it's your turn to get some practice. So let's go ahead and take kind of a short 3-minute break and have a work and have a look at this exercise here. So creating a new environment. So create an environment called machine learning env and install IPython, Matplotlib, pandas, scikit-learn. And also pip, don't forget pip. And then kind of see what happens. So so again, if it's everyone else is now saying it's taking a long time. So if you just hit Control C, that will kind of kill that process, and then you can just move on. I'm not sure why it's taking a long time. So take a look at this exercise, machine learning environment, and I'll give you kind of 3 minutes to take a look at that, and we'll come back and work on it together. So I'm going to stop sharing my screen, and then now I will solve the exercise, and then we'll check back in 3 minutes. Oh, sorry. The exercise. So the exercises are in the lecture notes on the working with environments episode. And if you scroll down, then you'll find the exercise there. All right, let me share my screen again. Okay, so in the introduction to Conda for data scientists, so the second episode is called Working with Environments. So these are the teaching materials that I've been following for the past 30 minutes or so. And if you scroll down, then you'll find an exercise on creating a new environment. So that's the exercise that I would like you to try on your own. Okay, can everybody find the environment? Or sorry, the exercise? So here's the direct link to the episode of the teaching materials. Okay. Yes, and pip. Don't forget pip. Okay, that was the timer, but I'll restart that timer because I feel like I just, right. So I will stop sharing my screen. And let me make sure I followed my own advice. And yes, I did. Okay, I installed pip. Okay. So we're going to take just a short break here. So I'm going to pause the recording, and I'm actually going to run and get a cup of tea, and then I will come back and we'll talk about this exercise. All right, so I'll be right back. Okay, we're back. So I will share my screen. So hopefully you guys had a chance to practice this environment creation command. So here's the command that I used. So I installed Python, IPython, Matplotlib, Pandas, and Scikit-learn, and it looks like I actually left off pip. But then if you scroll down through here, I noticed that pip actually gets installed. I did not expect this. So it's always good to explicitly list pip as a dependency. That way you'll be sure to get it. And there won't be any ambiguity or uncertainty as to whether you did. So a better command would have just added pip to the end of that. Okay. Okay, so now that we've created a bunch of environments, so the next thing that we want to do is to talk about how to activate environments. And the command to activate environments is simple. So it's the conda activate command. So if you do conda activate machine learning environment, actually before we run this command, let's look at which Python. Actually, I'm going to clear this out to give us more room. So if we run which Python, so we can see that we're using the Python in the notebook environment. So that was the current environment that we've created. So now if we do conda activate machine learning environment and hit enter, we are now switched to a different environment. And we can immediately see that because conda puts in parentheses machine learning environment as part of our prompt. So that's a visual indication of which environment is active. So now if we type which Python, my cursor is lagging here in the, there we go. Now, if we type which Python, you can see we're using a completely different Python. So the Python that we're now using is inside the machine learning environment, which is the one that we want. Okay. So environment activation it's a simple command, but actually the process that's going on behind the scenes can be quite elaborate. So when you activate environment, you do kind of two things. So one is you append entries to your system path variable. Your system path variable is just a list of directories in which your operating system should look for software. And by appending the directory by appending the directory of our Conda environment is the main way in which Conda controls which software we find. So for example, if we were to type echo $path, which is just going to print to the screen the value of this system path variable, you can see that so we have, these are system environment variable and paths, your home directory, and then the next one after that is actually the machine learning environment. So as we kind of go through these paths directories, the paths themselves are just separated by these little colons here. So we'll go through, the operating system will go through this from left to right looking for software. So when you type Python, it will first look there and not find it. And that's the same path. I'm not quite sure why that's there twice. And then it will look here and it will find it. And then similarly, when you import things, the import will look in this machine learning environment. It will know to look there and not in these other locations. Okay, cool. The other thing that can happen when you activate environments is that sometimes, particularly with scientific software, there might be environment variables that need to be set to particular values in order for the software to work properly. And the creators of the Conda package for that, or the Conda distribution for that software package might put these activation scripts, which will properly set those in variables for you so you don't have to do it yourself. But those scripts will be run in the background when you execute the Conda activate command. Okay, so if we wanted to deactivate the environment, we could just do Conda deactivate. You do have to spell your commands correctly if you want them to work. Deactivate, and then that will deactivate the machine learning environment in this case and put us back into the notebook environment. So you can see that the notebook environment is the active environment. And then let's see what would happen if we did Conda deactivate again. And now that has deactivated the notebook environment, and we can run Conda env list. And we can see that now actually the active environment is this base environment here. And then we can also see all these other environments that we've created. Okay. So there's some exercises on activating and deactivating environments. I'm going to just skip over those in the interest of time. I think you can get enough practice throughout the rest of the day on activating and deactivating environments. Okay, so now let's move on to installing packages into an existing environment. So there is a Conda install command. Which is used, if we go up to the top. So, we did Conda create, and then we provided the name of the environment that we wanted to create, and then we listed packages to install into the environment that we were creating. The Conda install command works kind of the same way. You've got Conda install, and then we're going to pass the name of the environment that we want to install into, and then a list of packages. Alternatively, you can activate the environment and then just run Conda install and then a list of packages, and that will install into the currently active environment. So let's see some actual examples of that. So I'm just going to clear this away. So for example, if we did Conda activate the basic SciPy environment. Okay, so now you can see that the basic SciPy environment is active. And now we could just do Conda install, and we don't need to list the name of the environment we're going to install into. It's just going to install into the currently active environment. And let's install a package called Numba. So Numba. So Numba is a package you should be familiar with if you're doing scientific computing, data science, machine learning, and Python. So it is a just-in-time compiler that will take your Python or NumPy code and compile it down into very fast machine code using the LLVM compiler stack. So here's an example right here where someone has written this pure Python Monte Carlo approximator for pi, and then has imported this little JIT decorator here. And then with this one line, well, 2 lines of code counting the import statement, then Numba will compile this Python down into machine code, and it will run basically as fast as if it had been written directly in C or C++. And Numba will target different hardware architectures. It will also target GPUs, so you can actually write Python code and then JIT compile it to run on a GPU. So it's a super cool package and library that you should definitely be familiar with. And we're going to install it into our basic SciPy environment with just once we activate the environment, we can do Conda Install Numba. And this will install the most recent version of Numba that is compatible with that can be installed into the existing environment. And we'll go ahead and say proceed, and yes, we hit enter. And so you can see we're going to get Numba 0.51. Okay, and that's it. So that's the installing packages. Okay, so now I want to take 3 minutes. And oops, that's not what I want. And I want you to install, there's a couple more exercises so to get some practice installing libraries yourself. So there is a link here to Dask. So I want you to install Dask into the machine learning environment. So Dask is a library for scaling kind of the standard data science stack of NumPy, Pandas, and scikit-learn, and scaling it so that it can run across multiple nodes in a computing cluster. So NumPy, Pandas, and scikit-learn will take advantages of all the cores that you have on your laptop or your workstation, or all the cores on a single node, but in order to single node in a computing cluster. But in order to scale horizontally across different nodes in a cluster, Dask will handle all the complexities associated with that. So it's a really great library to be aware of. And so the exercise in the same episode asks you to install Dask in the machine learning environment, and then also to install Combo using pip. So Combo is just an example of it's an interesting little package. It's not available via Conda, it's only available via pip. I just want you to get practice using pip install to install things into a Conda environment to understand that it does work kind of as advertised. It's a very popular package for doing what's called Ensemble Learning, or a particular type of Ensemble Learning. So it allows you to take different models and then combine these models to give a final prediction. And generally, the way these work is that you might have a bunch of simple models that are kind of wrong or underperform, but in different ways. But then if you average the predictions across these models that are both kind of wrong in their own different way, average prediction of those models might turn out to be really, really good. And so Combo is a nice library for doing that. And you can think about like combining the predictions of these models by either simple averaging, or if it's a classification problem, you can think of it as like a majority vote, or different things like that. So and it works really well with scikit-learn, but it's not available via Conda, or at least it wasn't available when the last I checked. So you can install it via pip. Okay. So let's take 3 minutes. I'll set the timer again. Have a go at those exercises, and then we'll come back and work on them together. All right, so I'm going to go ahead and stop sharing now, and then we'll come back and work on these in 3 minutes. Okay, and we're back. So I will start sharing my screen again. So we're going to go through just these 2 exercises. So the basic SciPy environment is active right now. So I'm going to go ahead and I'll do clear and Conda deactivate to deactivate that environment. Now I'll show you the alternative Conda install syntax. So I'm going to install into the machine learning environment Dask. And so instead of activating the machine learning environment and then just running Conda install Dask, here I'm explicitly saying I want to install Dask into the machine learning environment. So I'm just kind of demoing this alternative syntax here. Okay, and you can see Dask actually, as you might expect for a library that allows you to scale computations across multiple nodes in a cluster, there's a fair number of dependencies, more than, so just hit yes. Let's actually go back and just take a look at, okay, so if you look at the environment location, so if you were in doubt that we were installing into the machine learning environment, you could see here in the environment location that we are in fact installing into the machine learning environment as expected. So I'll just go ahead and hit yes, let Dask, or let Conda install Dask. Okay, and now if we do Conda activate machine learning environment, and I'll clear to get our, so now the machine learning environment is activated, and then if we wanted to check that Dask was actually installed, there's a couple of ways that we could do it. I mean, one, you could start up Python and do an import Dask. But jumping ahead a little bit in the notes, there's a command called conda list. If you run this, it will list out the contents of the current environment. So these are all the packages that are installed in the machine learning environment with their versions and build numbers and where the packages came from. The channel, that's the last column here. We'll talk about channels later. And if we scroll through here, we should see Dask. Yeah, there's Dask. Okay. So let's clear this out. So then the next thing was to install Combo with pip. So if we run which pip, we'll see that the pip that we're installing, or we're using to install, is actually from the machine learning environment. So that's key. So now if we do pip install combo, then pip will go and download combo. And I'll just wait till it finishes, and then I'll talk about the logging messages that we're seeing here from pip. Okay. Right, okay. So what you'll see here is that many of the requirements for combo are already satisfied. So it's, combo required joblib and matplotlib and numpy, but these are already installed in the environment, and so pip did not install them again. We did install Numba, but remember we installed it in the basic SciPy environment, not the machine learning environment. So here, pip installed Numba for us. And then these other dependencies that were downloaded were things that were either dependencies of Numba, which pip installed, or dependencies of Combo that did not already exist inside of our environment. And then we're done. Okay, and so now if we run clear, and then run conda list again, and now if we go through here, we should see combo. And you'll see like anything that says PyPI will be something that was installed via pip. And so there we go. So now we've had an example of how to install into Conda environments using pip. Okay. So moving on. So we've actually already seen the answer to the question of where Conda environments live. So I'm going to deactivate the machine learning environment. But if we run the command, so Conda environment list, then we can see the paths basically to where the directories containing the Conda environments with particular names live. We can also see, again, which is the active environment. In this case, it's the base environment. Notice that all of the environments that we've created start with / in this case, srv/conda/envs. So this envs directory is where is the default location on Binder for Conda environment. So if you create a Conda environment, it's going to be installed as a directory within the envs directory. Now, if you've installed Miniconda locally, then the default location is like your home directory /Miniconda3/envs. And it's a little bit different here on Binder because of the Binder team has their own schema for installing software. Now, there are good reasons why you might not want to install your Conda environment into a directory that is in this default envs directory. In particular, I find that it's a best practice to install the Conda environment in a subdirectory of your project directory. So all my projects have their own project directory, so I keep all my project files in one place. I don't, just everything's in one place. It's easier to keep track of my research that way. And then within that project directory, I will always have a env directory where my Conda environment lives for that project. So that way, even my software stack is right there where I need it in my project directory. So let's see an example of how we could create a Conda environment and specify a particular directory. So the first thing we need to do is create a project directory. So, so right now, if you run pwd, we'll see that we're in our home directory. And if we run ls-f, we can see what is here in our working directory, and if we, in particular, there's this introduction to Conda directory here. So let's change into the introduction to Conda directory. And now if we run ls, this is empty. So this is just an empty directory. And so in here, we'll create a project directory. So if you had come along to the bash training or you watched the bash training on YouTube, then you would have learned there's a make dir command, which you can use to create a directory. So I'll just call this my project directory. Now, if we run ls-f, we'll see that there's a my project directory there. And so we can change directories into the my project directory. Okay. So now we're in our project directory. That's the idea here. And so now we're going to run a conda create command, but instead of specifying a name, we're going to provide a prefix. Now the prefix is basically the path to a directory which will contain our Conda environment. So I like to put Conda environments in a directory called env, and I like it to be within my project directory. So I need to specify the path, and it can either be a relative path. So I can specify a relative path by using dot slash to specify the current directory slash env. You could also use $pwd, which will be the path from the root of my file system down to my project dir slash env. Either of those will work. I usually do dot slash env and use a relative path. And so now we can list off the things that we want to install. So we can put, let's do Python, IPython, Matplot. Actually, so in Bash you can do multi-line commands with a backslash. And now I'll just type Python, IPython, pandas, Matplotlib, let's not forget pip, and then let's put scikit learn, maybe Dask, and Dask. How about that? That's good enough. And then hit enter. And so now it's the same process that we went through when creating environments by name, except now this one is going to be created and installed not into the default envs directory. It'll be installed in a subdirectory called env of our projects directory. I'll show you that in a minute. Although if you scroll up here, the environment location, note that this is not the kind of default, not into a subdirectory of the default location, envs directory. It's in the particular directory that we specify. Okay. Okay, great. And so now we're done. So we can clear, and now if we do conda env list, you'll see that we have this directory that doesn't have a name. Its name is basically blank or null. And then it has a path to this environment subdirectory. And now if we want to activate it, instead of providing a name, we don't have a name to provide. So instead we just provide the path. And now we have this huge prompt, which is a bit cumbersome. I'll show you how to change that in a minute. But you can see that this is the path to the active environment. And if we were to run a command like which Python, we'd see that the Python that we get is the Python in the env/bin directory. Okay. A nice thing, so if you follow this best practice convention that I'm encouraging, where you install, like I did here, via prefix into a subdirectory in your projects directory, specifically called env, then if you use git to version control your projects, the standard python.gitignore file will ignore the env directory. So you don't have to worry about accidentally version controlling this environment directory, which might have quite a lot of stuff in there. But the important thing is for your own sake to be consistent. So if you don't want to use env and you want to use some other naming convention, that's fine, but just be consistent with your naming conventions. It will help you later. Right, so I wanted to show you how you can shorten this prompt up a little bit. So Conda has a configuration file that you can, that you can use to kind of configure various different aspects about Conda. But one thing that you can do, so if you do Conda config help, it gives you some information about how to make modifications to your configuration file. But in particular, so I'm going to clear this out. So one of the things that you can do is you can use --set to set a particular configuration key to a particular value. So in this case, we're going to set the environment prompt key to a particular value, and it's going to be a little bit cryptic. But if we do this, and then we can probably have to deactivate and then reactivate. Yeah. So notice that instead of having this long explicit path to the currently active environment, we just get the name of our environment. And since our environment doesn't have a name, Conda basically takes the name of the directory containing the environment as the name, kind of in inverted commas. So what you gain in terms of a shorter prompt, the cost of that is that now you just have this generic thing here as opposed to an explicit path to your directory. So you can, it's kind of up to you whether you want to do that or not. There are other ways that you can shorten paths using bash settings, where you could shorten this long bit to something shorter. Generally, it's not a big deal, and I don't often do this. I don't often set the environment prompt like this in my own work, but I thought it was worth showing you. People have asked about it. Now, what has happened here is that by running this conda config command, if we list the contents of our home directory, you'll see now that there is this .conda rc file. That's the Conda configuration file. And if we were to cat the result, the Conda rc file, running that conda config command basically just put this key with a colon and then gave it this value. And so the conda config file is just this keys and values, and you can manually edit the .conda rc file to put your keys and values, or you could use the command line like I showed you here. There's a link to the documentation in the lecture notes on the conda rc file, or on the conda configuration file rather, if you want to know more about how to do that. Okay, so I would like you to practice creating an environment by prefix. So if you go in the environments, the same episode we've been working in, there is another exercise on creating an environment as a subdirectory within a project directory. So follow these, go through this exercise, maybe three minutes, and we'll come back and we'll work on this one together. I want you to get some practice creating environments by prefix instead of by name. Okay, so I'll stop sharing. I'm also going to pause the recording, and we'll be back in 3 minutes. Okay, and we're back. Right, okay. So I asked you to create a environment by prefix. So let's share my screen. Okay, so in particular, I had you create a environment for TensorFlow 2.1. So this is a slightly older version of TensorFlow now, but let's do this anyway. So the solution, is there. Like, you can toggle these solutions to understand what the solutions are. But let's go ahead and create this this environment anyway. So first, I'm going to change into the parent directory and create a new project directory. So I'll call this so tf projectdir. And then I'm going to do, I'm just toggling up to that Conda create command. And then, because it's the same command, I'm just going to use the create within a env directory within my project directory. And then I wanted to install particular versions of these things. So let's actually I'll leave off the version numbers, and then we'll see what happens, see what more recent versions are available for these things. So Python pip matplot, write this so you guys can read it more easily. So Python pip matplotlib and TensorFlow. Okay, let's see what happens here. Okay, let's check our version numbers. So, interesting. It seems to want to install an even older version of TensorFlow. No, it's TensorBoard rather, but this is now installing TensorFlow 1.14. So let's see if we can make it install a more recent version. So I'm going to say no. And then with TensorFlow, I'll just put TensorFlow 2.1 and hit enter. So this is saying that it wasn't able to find compatible packages in the first place that it checked, the first repo data source that it checked. So it's going to check another one. So this solving environment step sometimes takes a while. And one of the things that you can do to speed it up is actually to specify all your version numbers explicitly. Because by the more constraints you supply on the version numbers, the less work Conda has to do to find all of the potentially the dependencies. So here we go. So it found a newer version of TensorFlow 2.1 and everything else. So we'll just hit yes. And actually, let me go and see what version of say Python that it picked up as an example. So it got Python 3.7, pip 20.2, and then the other one I asked for was Matplotlib. So it also got a newer version of Matplotlib. Okay. So we're overdue for a longer break. So I'm just going to push quickly through to show you how to delete environments. It's the last thing that we need to cover in this episode. And then we're going to take a break for 15 minutes, and then we'll come back and pick up with the rest. This episode covers a lot of ground, and there's a lot of kind of explanation of what the commands are doing and things. So it usually takes a good while to get through this episode. The other episodes move much more quickly because we've covered a lot of the basic groundwork at this point. So TensorFlow, I guess, in case you're not familiar, so TensorFlow is one of the, I don't know, 2 or 3 big libraries for doing deep learning. So it's developed from Google. The other one is PyTorch that has been developed by Facebook, and then there's MXNet, which was maybe from Microsoft, or I can't remember where MXNet came from. I mean, they're all open source now. But have their own kind of corporate backers, basically, that provide a lot of the resources for development of the library. So TensorFlow has been one of the libraries that used to be very challenging to get installed properly, but now with Conda, it's actually quite straightforward. Okay, so we've done that exercise. So you can use Conda to manage, I'll just mention in passing. So there's an exercise here about managing R projects with Conda. You can manage your R dependencies with Conda. However, like the R community is kind of sufficiently separate within the data science and machine learning ecosystem that it has its own tool called PackRat for managing R dependencies. And so if you're within the R community, I would check out PackRat. Is anybody here interested in R? Use R regularly? Should I provide the link for PackRat, or is that not something that's relevant? Any R users? Guess not. So I won't bother with PackRat. Okay, so we covered the listing existing environments command already, and how to, the list environment, existing environments, and the list the contents of environments. So we've done that already, so I won't cover that. So deleting environments. So if you want to delete an environment, so if you're not using an environment anymore, you might as well delete it. No use keeping it around and cluttering up your disk space. So you can do Conda Remove, and then the name of the environment that you wish to remove, and then you need to pass -- all, so it will delete all of the environments, or all of the environment, including all the packages inside of it. So if we were to do, so I'll clear this out, just demonstrate this. So if we did Conda env list again, and you can see all of the environments. Our currently active environment is the my project dir environment. I'm just going to go ahead and deactivate this environment. So if we run this command again, we'll see that now the base environment is the active environment. And we can do Conda remove, and let's go ahead and remove the Python 3.6 environment, and then -- all, because we want to remove all of the packages in addition to the whole environment itself. So I needed to provide, I did not say that the name was Python 3.6. By running this command, it tried to remove this package as well as all the other packages from the current environment. And Conda won't let you do that because it's probably a mistake when you repart, which it was in my case. So we put name, and then it will prompt us. It will say basically, do you want to remove all the packages in this environment? And these were all the packages that will be removed. So I will say yes. And now if we do conda env list, we can see that the Python 3.6 environment is gone. So it's not there anymore. Okay. So we've covered all the basics. So we're going to take a 15-minute break, come back at 3:30. And then in the next episode, or like the remainder of the day, we're going to cover the environment files that I was discussing earlier, and then some examples of GPU dependencies, and then we'll do some Q&A. Okay. All right, great, thanks. So I will see you in about 15 minutes, so at about a little after 3:30. Oh wait, so we have a question in the chat. If you want to remove one package in an environment, that's a good question. So let's see an example of that. So let's suppose that, all right, so let's conda activate .env. So I'm currently in my TensorFlow project dir. So let's activate that TensorFlow environment. And so if we do conda list, so we'll list all the things that are in this TensorFlow environment. And let's suppose that we wanted to use a different plotting library. So we didn't want Matplotlib anymore. So let's remove Matplotlib. So we can do Conda Remove, and we'll look at the help menu for this. And so the example that they give at the bottom is how to remove SciPy from an environment called my environment. So that's basically what we're going to do. There is, and that's basically it. I was going to see if there was some other option that I wanted to do, but nope. So let's do conda remove. And since we're going to remove from the currently active environment, we can actually leave off the name of the environment, I think. Let me double check. Yeah. Yep. So we'll do conda remove matplotlib. And this should go and remove matplotlib. Plus, I think it will remove all of the dependencies of matplotlib that are not also a dependency of some other package that is installed. But we'll check and see. That's a good question. Right. And so you can see that Matplotlib has a lot of packages that are dependencies that aren't used by any other package. So basically, there's a lot of stuff that's just related to Matplotlib that isn't really needed in the environment if you're not going to use Matplotlib. And so you'll slim down your environment quite a lot. Okay, so now if we do conda list, we can see, so these are all of the things that are installed in the TensorFlow project. So including, there's TensorFlow. And yeah, so that's how you remove a particular package from a Conda environment. Good question. Okay, so now we'll come back in 15 minutes at 3:35. Okay, all right, great. So I'm gonna, okay, we're back. So there's a question that came in over the break. about if Matplotlib needs LaTeX, can I use Conda to manage it for me, or will it only manage Python packages? So this is a great question. And it's something that I can't emphasize enough. So one of the strengths of Conda is that it can manage dependencies for many different programming languages simultaneously. So if your workflow needs not just Python, but like Python, like for example, many bioinformatics, you might have Python, Java, C, C++, a whole mix of languages. Python can manage dependencies for all of those programming languages. In this particular case for LaTeX or LaTeX, yes, you can get. There are many different distributions of LaTeX or LaTeX available, and you can search for them either via Google or the Conda Search command and install them. So this happens like sometimes Matplotlib does need LaTeX to render certain types of plots if you want to save them in certain formats, I think. But for what LaTeX is required for, just for regular Matplotlib to work, Matplotlib, when you install Matplotlib, it will install kind of whatever basic LaTeX it needs to do what it needs to do. But if you need, sometimes there are additional packages that you might need to install depending on what file formats you save your plots in and things like that. I didn't look, so I think we have a list of things. So I think in the Matplotlib base package, there is some stuff related to LaTeX plotting, or not plotting, but like a LaTeX rendering of math equations, because you can use LaTeX to put LaTeX formulas into your plots and render them with Matplotlib and things like that. Okay, but we are moving on. Okay, so we're going to move on now to the next episode. So let me share my screen. Okay. So sharing environments. Let me get my other screen set up. So we've covered all the basics, and now we're going to talk about sharing environments. So in this episode, I want to answer the question of, why should you share your environments, and then how do you do it? And at the very end, we're going to hit on a little bit of a sidetrack, but we'll show you how to link up your Conda environments inside Jupyter Lab, so you can launch notebooks and IPython kernels and things like that from within in Jupyter Lab. Okay, so working with environment files. So I've mentioned environment files several points already, and I haven't really dived into the details. So in this episode, we're going to get into the details of environment files. So an environment file is a file that's written in a language called Yaml, which is just a structured text language, one of many. It's kind of like Markdown would be another one. YAML has become very popular for writing configuration files for web apps. It's obviously used here for environment files for Conda. It's used by Docker and Kubernetes and other kind of big industry tools for configuration files and things like this. So it kind of has the flavor of like key value syntax. So there's like a key. The first line of your environment.yaml file will always be name, colon, and then either the name of your environment or null if you are not going to name your environment because you're going to install via prefix. And then you have dependencies, and then you kind of list the dependencies, just like this. YAML is like Python is white space sensitive. So it doesn't matter how many white spaces you use. So like here, there are 2 white spaces, but what matters is that you're consistent. when you're formatting your environment.yaml files. So let's create an environment from an environment.yaml file. So what I'm going to do is I'm going to copy this third version of the environment.yaml file. So this first one basically has a name and doesn't list any version numbers. The second one shows you how you can put the name of null if you want to install via prefix. And the third one is has version numbers. So I'm just going to copy that. And then what I'm going to do is I am going to go into Introduction to Conda, and I'll just create a new project directory, and I'll just call this my other project. And then inside this my other project, I'm going to create a new text file. And here I'll paste the contents of my environment.yaml file. And then I'm just going to do right-click, rename environment, and then .yml. And then once I hit enter, JupyterLab will detect that this .yml is likely a YAML file, and it will do some nice text formatting and highlighting and things like that. Okay, so then we'll just save it. And now we'll come back here to our terminal. And so I'm going to clear. And then I'm going to do, I'll just hit change directory, make this a little shorter so you guys can see it, and then 2 dots to change into the parent directory. And then I want to deactivate any active environment. And so if I run ls, you can see that here's this my other project. So I'm going to change into that directory. And you can see there's that environment.yaml file. And so now I'm going to run the environment creation command, which is now slightly different because we're going to use an environment file. So it's Conda, instead of Conda create, it's Conda env subcommand create. And then we'll do -- prefix, and then /env, just like we did when before. And then we specify a file to use, environment.yaml. And that's actually the default value for this -- file parameter, but I just am in the habit of typing it. So I just always type it out explicitly. And then we hit enter. And now what will happen is at this point, basically the exact same sequence of events that we've seen when we've been creating projects or creating, Conda environments before. It's just that instead of manually typing out a list of packages and things that we want to install, Conda is inferring that information from the environment.yaml file. And using these environment.yaml files is a Conda best practice. So I always use environment.yaml files. And it helps, again, for reproducibility. I can share this file with my research colleagues, peers, teammates, and they can reproduce the software stack on their machine much more easily. And I can also port my software from my local laptop and workstation to remote computing clusters by just copying the file and then running the Conda command on the remote server or compute cluster. And you can see over here, so here is this env directory that's been created. And I'll take a look at it once we're done here. Okay, so now we're done. So if we look in here, you can see that there's actually quite a lot in here. And the details of this are not particularly relevant for you as a user. If you're building Conda packages to distribute your own software, then you have to understand kind of some of these internal implementation details, because your package needs to install things correctly, given the schema of the environment directory. But for us as users, we don't need to bother with that. Okay, so that's it. So that's like that's the key command that I use to install or create Conda file or Conda environments from environment.yaml files. So if you don't have an environment.yaml file, you can create one from an existing environment. There's a couple of gotchas. There's this command conda env export. There's a few gotchas with this. One is that it generates environment files that are very, very specific. I'll show you what I mean by that in a minute. The environment files that are generated by this may not be portable across operating systems, because they will have packages. If you run the command on Linux, they'll return installed packages that might only be available for Linux, because they're Linux OS specific requirements. And so you wouldn't be able to give that environment file to a Windows user or a Mac user, and it would probably not work. Sometimes you can get around that problem by passing this no builds option. But even then, it's not entirely straightforward. Where this command is super useful is if you need to share an environment.yaml file with someone who's running on the same operating system. So for example, with when I work with CALST users on IBEX, and I'm trying to when I'm trying to debug a problem that they're having with their Conda environments or with their software stack, I will ask them to run the Conda env export command and send me the environment file. So that way I can reproduce exactly what the exact environment that they have. So I'll show you what happens if we were to run this this command. So let's run it on. Well, actually, we'll run it on the we have here. So we'll run just conda env export. So this is going to create an environment file from. Need to activate the environment first. So let's activate environment. Oops. Conda activate the environment, and then run conda env export. Invalid environment name. Was not expecting that. Okay. Well, let's just run this on another. It's a command that I don't use often. So let's just run it on another environment. So let's deactivate the current environment. And then let's activate let's cd into parent directory. I'm going to run clear just to get some space back. And then let's do Conda environment export for machine learning environment. Get rid of this. Okay. Now what you can see here is that we get the output that we get is, you could copy and paste this into a text file and it would be a valid environment .yaml file. We can actually redirect that into I'll call this exported environment.yaml. And this is going to redirect this output to a file here. And so you can see that these versions are quite specific. It includes both the version number and the build number for everything, all of the packages that are installed in the environment. Now, if you pass the same command, but with the no builds option, you can sometimes get an environment file that will work. Notice that it doesn't have the build numbers anymore, only the version numbers for the packages. But you still might have packages that are operating system specific, in which case you wouldn't be able to use this Conda env export command to create an environment file that you could share. So the takeaway from this is that you really should get in the habit of creating your own environment.yaml files whenever you start a new project, and keeping them in the root directory of your project directory, basically. Okay. So now it's your turn. So let's take 3 minutes and have a go at this exercise here. So creating a new environment from a YAML file. So here I've created a YAML file or environment.yaml file for you for a project that includes a tool called XGBoost. XGBoost is a very, very popular and widely used, probably the most widely used machine learning library or machine learning model in industry. So XGBoost is short for extreme gradient boosting. So it uses algorithms called gradient boosted machines to solve regression and classification problems. It scales really, really, really well, both on CPUs and GPUs on a single node or multiple nodes. And so it can attack pretty much any machine learning problem that you're likely to encounter. It also has a lot less complexity than your standard kind of deep learning approach or libraries. So it tends to be very, very widely used. So now you're going to create an environment for XGBoost. So I'm going to stop sharing my screen now. And just to make sure that there's no trouble finding the exercise, I will paste it in the chat. So the link to the current episode we are working on. Okay. All right, so go ahead and take a few minutes to have a go at that, and we'll come back in 3 minutes and I'll go over it together. All right, about another minute to take a look at that exercise. Actually, not even in a minute. Okay, so I'm going to go ahead and share my screen again, and we'll go over this one together. So instead of copying and pasting this, I'll actually just create it from scratch. So I'm going to come over here and I'm going to create a new project. And I'll call this XG Boost Projector. And then inside here, I'm going to create a new text file. And I want to have name, I'll put null, and dependencies. I'm going to put IPython, sorry, only one dash, IPython, I like 2 spaces, Matplotlib, you can put space after his if you want, pandas, pip, Python, scikit-learn, and XGBoost. And I'm going to leave off the version numbers because I'm actually curious to see where the versions have evolved since I last installed, or I last built these lecture notes. Let's see if I can try to restrict this version of Python to be at least Python 3.8. So I'll save that, and then I'm going to rename accordingly. Okay, so now I've got my environment.yaml file, and then let's clear this out. And so it wants to change directories into the XGBoost directory. And then we're going to run that command. So conda env create. And we're going to put it in a subdirectory, call it env. And we're going to create it from environment.yaml. And then we'll take a look and see what actually gets installed, what version numbers get installed. So it looks like the newest version of XGBoost is 1.2. And note that XGBoost has dependencies. There's 2 things about XGBoost. So here's the Python bindings for XGBoost. Then there's this lib XGBoost, which is actually the C++ library that does all the work. And note that scikit-learn and scipy were dependencies of XGBoost. We didn't specify or ask for those explicitly, but they were installed because they're dependencies of XGBoost. So if we do conda activate our environment, and then we could do Python, and then if we just wanted to test, we could do import XGBoost as XGB. And there we go. So that's just a quick test that this did in fact import or install XGBoost as we had wanted. Okay. So what if you want to update an environment? So if you want to update environment, there's basically there's 2 ways that you can do this. So one is that there's actually an update command. So you can make whatever changes you want to your environment.yaml file. You can add a package, you can remove a package from the environment.yaml file, and you can run this update command here. What I typically do is actually, I just remember this one command. So I just rerun the create command with a -- force, which completely deletes the existing environment and then rebuilds it from scratch. It takes a little bit longer, but not like that much longer. And I found that the ability to kind of just burn down your entire environment and then rebuild it from scratch whenever you want is really powerful. And so I like to do it. It helps me like maintain kind of confidence that I know exactly what is installed in my environment. So let's install Dask. So if you want to scale XGBoost across multiple nodes more easily, you can do that with Dask. So let's go ahead and install Dask. And we're going to do this together in the interest of time. So what I'm going to do is I'm going to go to my environment.yaml file, and I'm just going to add Dask as an extra dependency. I'm going to save. And then I'm going to run, well, I'm going to deactivate. And then I'm going to run the environment creation command again. So it's kind of gone over onto another line, but I need to add the -- force, because if I don't add that, Conda will complain and say this environment already exists. Do you want to overwrite it or not? So I'm just going to say force, do that. And so now I'm going to recreate the XGBoost environment completely from scratch. If we watch over here, yeah, so you can see the environment directory's already been removed. The first thing that was done was that directory was completely deleted. And now we're going to rebuild it from scratch. So it's another handy command to be aware of, so that if for whatever reason somehow you corrupt so both it's a handy command, but also working with environment.yaml files is really useful. If you somehow, some way corrupted your Python environment, then you could just burn it down and rebuild it again from scratch using this command. And that's really handy. Okay. So now we've got Dask installed. And if we activated the environment, and then we did a Conda list, we'd see that Dask is here. Okay. So now, what's next? Okay, so the next thing I want you to do is, or I want to show you how to do, is launch Jupyter notebooks and IPython consoles from a Conda environment. So if we go to Jupyter Lab, and so these notebooks here that you can launch here, these are tied to the notebook environment. They're not tied to any of the environments that we've created. So they won't have a lot of packages that we have installed. So for example, like if we try to import TensorFlow as TF, there's not any module named TensorFlow in this environment. So if we want to use Jupyter notebooks or IPython consoles like this for environments that we've created, we need to create what's called a custom Jupyter kernel for our Conda environments. And so that's what I'm going to show you how to do right now. So, and this is in the section making Jupyter aware of your Conda environment. So the first thing that we need to do is we need to add this IPyKernel package. So that's the package that actually creates the kernel specification file that Jupyter will use to connect your Conda environment with Jupyter notebooks and or with the Jupyter lab that's running. So we need to install that first. So let's do that. So I will change into introduction to Conda, and then my XGBoost projector, and then I can do two things. So I could either go in here. Well, I should definitely go in here and add IPy kernel and save. Now I could just run that command and recreate the environment from scratch. So I could do conda env create prefix environment file and then we'll run it yet again a third time, same command, and we'll install the IPy kernel package. You could also have activated the environment and then done a Conda install IPy kernel, but then you need to remember to go back and add the IPy kernel package here to make sure that it would get installed the next time that you rebuilt the environment. So again, I am willing to trade, order of a few minutes of build time to rebuild the environment from scratch for the clarity and sanity of kind of always knowing what the state of my environment is, because I always have this record in this environment file of exactly what I've installed. And that's kind of a hard lesson learned from experience. But then when that's done, then after we activate the environment, then we have this command here that we're going to run. And that's going to create the kernel spec file, which Jupyter will then detect and then create notebooks and IPython console buttons so we can launch notebooks and IPython consoles that are attached to this Conda environment. And this name is just kind of an internal name, and this is the display name actually controls what you see in Jupyter Lab. So I'm just going to copy this command. And okay, so I need to activate the environment. So you need to make sure you activate the environment so that the kernel spec file is generated for your environment, because it will generate the kernel spec file for the active environment. So we can just paste this command, and I'll change this to be XGBoost in. I'll hit enter. So creating this this kernel spec file does not take very long. And now if we go back, we can go to our launcher, and you can see now there is notebooks and IPython console. So if we were to launch a notebook and we were to run import XGBoost as XGB, then it works as expected. And I'll just close this and don't need to save. And I'll just delete it. We don't need to keep it around. Okay. So there's an exercise here. So let's see if you guys can create a custom kernel for the machine learning environment. So remember, there's three things that you need to do. You need to install the IPy kernel package into the machine learning environment. And then you need to run the command to create the custom kernel, and don't forget to activate the machine learning environment, obviously certainly before you install the IPy, or you generate the kernel spec file with IPyKernel, but also probably before you install the IPyKernel package. Okay, so I'll set the timer for 3 minutes, and then we will reconvene and go over it together. Okay, and we're back. So let's take a look at this exercise. Okay, so we're going to create a custom kernel for the machine learning environment. So let's get rid of that. Okay, so I'm going to deactivate the environment that I currently have active. And so the first thing we need to do is activate the machine learning environment. And if we do a Conda list to see what's installed, I don't think the IPyKernel library or package is installed, but let's just check. No, it is not installed. So we will install it. So let's do Conda Install IPy. And we'll just say yes. Okay, now that we're done, so now we're going to run the same IPyKernel creation command. Okay, and now if we go back to our launcher, we can just keep hitting the refresh button, and eventually, there we go, machine learning environment. And if we go here, so scikit-learn is there. So if we opened like an IPython console and we did say from sklearn import the cluster module, then that would work as expected. Okay, so there we go. Okay, so that was kind of the second big lesson that I wanted to cover. Creating environment files, how to create environments from environment files, how to update environments using environment files, how to create custom Jupyter kernels. So the next thing that I want to do is, I think I'm probably, in the interest of time, I'm going to skip over packages and channels. Packages and channels, so this dives into more detail about what a Conda package is, beyond it's a precompiled binary statement. If you're interested in more details, particularly if you think you might have software that you've created and you want to distribute it via Conda, you would probably need to go and familiarize yourself with the contents of this episode. And then Conda channels, a Conda channel is basically where, if you have been wondering, like, where does Conda find packages to download from the web? And the answer is, well, it has particular channels, which are basically URLs that it looks at to download those packages. And so there's more details about that in here. But instead, what I want to do is talk about managing GPU dependencies. So just really quickly, in the participants menu, so how many of you are currently using GPUs as part of your research or your work here at KAUST? Or if you're not here at KAUST, then same question. Okay. So only one of you, I see. So how many of the rest is there? How much interest is there in learning how to use GPUs? Like, is using GPUs something that you would be interested in doing in the future? You just haven't gotten around to it yet. We have some really great GPU computing facilities here at KAUST, so it's really to your advantage to know how to leverage GPUs for your research, for sure. Okay. Okay, so then what I'm going to do is I'm going to cover, I think, probably half of this, and in particular, I'm going to cover the how to get the NVIDIA libraries that you need via Conda and some examples of that, but I'm not going to cover the more advanced topic of what do you do when you need the NVIDIA CUDA compiler, basically. And if you have questions about that, you can ask them, because I want to leave some time for Q&A. So it'll take me about maybe like 15 minutes to cover the first half of this, this episode, and then that leaves us about 30 minutes for Q&A. Okay. So managing GPU dependencies. So this is a use case where Conda really shines over the alternatives. So the first thing we want to do is get familiar with what CUDA libraries are required. So if you're going to use GPUs, then there are a whole new sub ecosystem of libraries that you need to be able to install and manage in addition to your normal CPU-based software. There's things like the Nvidia CUDA Toolkit, which is the main one. I put a link to that here. It'll take you to Nvidia's website, and you can see all the details and documentations about the Nvidia CUDA Toolkit. If you're doing multiple GPUs, then you want to use Nvidia's collective communications library. It's called Nickel, which will help optimize the communication between the GPUs and take advantage of the sophisticated hardware that we have here at KAUST, and that also is available in the public clouds for doing multi-GPU communication. And then if you're doing deep learning, then you'll definitely want NVIDIA's deep neural network library, CUDNN. So these are kind of like 3 libraries that you need to download and manage. So let's see how we can find these with Conda. So I'm going to clear all this out. And I'm going to deactivate environment. Okay. So let's use the Conda Search command. And let's look for CUDA Toolkit. And I'll put a star at the end. So anything that starts with CUDA Toolkit. And let's see what comes back. Okay. So we have from the main channel, which is kind of the default place where Conda looks for software installs, we have different versions of the CUDA Toolkit. So 9, 9.2, 10, 10.1, 2 versions of 10.1, 2 different builds for 10.2, and then 11.0, which is the most recent the most recent version of the Conda Toolkit. Now, on the Conda Forge channel, Conda Forge is kind of the community-based channel for Conda. It's like similar to CRAN in the R ecosystem. And it has also lots of stuff, including a bunch of Conda Toolkit dev. So the difference between Conda Toolkit and Conda Toolkit dev is that the Conda Toolkit dev version actually has the Nvidia Conda compiler. So if you need to compile custom CUDA extensions that either you've written yourself or that some library has provided but need to be compiled in order for you to use them, then you would need to get the Conda Toolkit dev package rather than the Conda Toolkit package. But both are available via Conda. Nvidia actually also has their own channel. And if you search and you put in channel Nvidia, then you will also get results for the Nvidia channel. And you can see that there's a lot of overlap between packages that are available on main and packages that are available on Nvidia. In fact, they're basically, the build numbers are often the same. So like this is the same package. It's the same build. And that notice that Nvidia does not distribute Conda Toolkit versions that have the compiler for reasons that are not obvious to me. Okay, so we can do the same for cuDNN. So remember, this is the Nvidia's deep neural network library. And you can see that, again, there's a mix of main and Nvidia channels, but they more or less have the same versions. But one thing to note is that the cuDNN versions, for example, 8.0.4, there's like 1, 2, 3, there's 4 versions, 4 builds of 8.0.4, and that was because the different builds map to a particular version of the Conda Toolkit. And so you have to install a cuDNN that matches the underlying Conda Toolkit version that you're using. Conda will manage all this for you. I'm just mentioning it for your own understanding. You don't need to worry about this directly yourself. And again, we can do the same with Nickel. And see that there are no actual, or there are very old versions of Nickel available on main. Most of the newer versions are available on Conda Forge, or obviously you can get it from Nvidia directly. Okay. So let's see. So we've covered basically how to get the Nvidia library. So let's see. Let's see some examples. So here's an example of how to build a PyTorch environment using Conda. So Conda is actually the recommended way to install PyTorch. The official PyTorch binary actually ships with Nickel and cuDNN compiled with the PyTorch binary together. So you don't actually need those here. So let's see an example. So I'm going to copy this, and then we're going to go through the same process again. So I'm going to create a PyTorch project dir, and inside here I'm going to create a new text file. I'll paste the contents. Environment.yaml. And then I'm actually just going to go through here and again, just delete the version numbers to see what I get as the most recent versions. And actually, PyTorch has some other things now. So there's like Torch text for doing NLP, and Torch audio for doing audio processing. And you can also install TensorBoard. So TensorBoard is supported directly now within PyTorch. So if you want to monitor your training progress with TensorBoard, you can do that. So I'll just add those in there. Now note the channels. So PyTorch actually has its own channel. And so we list the PyTorch channel first to give, which will make Conda look in PyTorch channel first for all of these dependencies. And it will install, in particular, PyTorch and Torch Vision and Torch Text and Torch Audio from the PyTorch channel. And then the others it will install from probably Conda Forge or maybe the defaults channel. And so let's see what we get with this. So I'm just going to clear, and we're going to change into the PyTorch project directory. And again, we're just going to run that same command. So conda env create prefix, oops, -- prefix. And right. And so this is going to create our PyTorch environment. Kind of a fairly reduced form PyTorch environment. And while this is building, so we're getting close to the end, I want to draw your attention to so the Calst VizLab GitHub repository. So I maintain a number of template projects to help you get started with managing your own software stacks with Conda, and I've kind of broken them out according to whether you want to do scikit-learn or PyTorch or TensorFlow, or Nvidia Rapids is a GPU accelerated software stack similar to scikit-learn, or Horovod if you want to do large-scale distributed deep learning over many GPUs on many nodes. So I've kind of set these up to get you started. So like if you pick one of the, like the PyTorch project, for example, like I have all of the configuration files, like the environment.yaml file, already set up and ready to go. And all you have to do is basically run the commands to create the Conda environment, and you can create template repository based on this setup here. You can clone it onto Ibex. You can use Conda and create your environment, and then you'll be ready to go, basically. Okay. So over here, it looks like, kind of looks like it's still going. I'm not sure what is. There we go. So you can see, so actually the most recent version of PyTorch uses Gpu Toolkit 11. And I'm still waiting to get the most recent PyTorch version. I think it's probably going to be 1.7. The CPU versions of PyTorch are also accelerated by Intel's math kernel library. So that's this dependency here that you see there. I'll come back and check on this. So I've got another example here for TensorFlow. If you want to take a look at how to install an environment.yaml file for TensorFlow with the GPU version. Unlike PyTorch, cuDNN and Nickel are not distributed with, or not compiled together with TensorFlow, so you have to install them and make them available separately. So that's why they're listed here. And then I had mentioned Nvidia Rapids. So Nvidia Rapids it's a GPU accelerated software stack that is modeled off of scikit-learn and pandas and Dask. Actually uses Dask, and it's becoming very, very, very popular in industry right now because it dramatically speeds up using GPU's kind of mini classic machine learning algorithms. And highly recommend that you check it out since we have such great GPU computing resources here at CALS that would make sense to kind of try to leverage them whenever possible. So there's an example of an environment.yaml file for that. And then also there is a corresponding Nvidia Rapids project template, which has the same or similar things. Still downloading over here, PyTorch. But PyTorch 1.7 is the most recent version. These are some big downloads if you look here. So these are actually the compressed files that are being downloaded. So this is 622 megabytes compressed for the CUDA toolkit. The same 660 some megabytes for PyTorch itself. Again, because PyTorch has compiled cuDNN and Nickel together with its own binary. So that kind of explains why it's so large. And then MKL is also quite big, 213 megs compressed. And maybe we have a bit of a slow internet connection between wherever this compute is running and the wider interwebs. Okay, and then the rest of this is kind of exercise for you, the participant, if you need to use the CUDA compiler. You can always reach out to me with questions if you're having issues with this. Kind of walks you through first, try to download the CUDA Toolkit dev package, see if it exists for the version of the CUDA Toolkit that you need. Some examples here on using PyTorch cluster, or PyTorch cluster is an example where you need to compile some custom CUDA extensions, and so you need the compiler for that. Shows you how to integrate Conda and pip in the environment.yaml file, which is something that we didn't talk about. You can actually just put install pip like this, and then for pip you can just list this one line, which looks a bit cryptic, but what it does is it basically allows you to then list your pip dependencies in this requirements.txt file, and then Conda will basically just install everything listed in the requirements.txt file using pip after it builds the Conda environment, installs everything else in the environment.yaml file with Conda. And then there's a separate approach for if you can't get the version of the CUDA compiler that you need from the CUDA Toolkit dev package, then you can install the version of the CUDA Toolkit from Nvidia on your system yourself, or you can take advantage, if you're on IBEX, you can use the system modules that make different versions of CUDA available. You can use that module, and then you can use this NVCC package to make your Conda environment aware of the system installed CUDA toolkit. So there's two approaches for doing that. Again, they have more advanced use cases, and I'm happy to entertain any questions about them for anybody who might have them, but they're quite detailed examples. The motivating example for this last section goes through a build of Horlod, which is a library for doing distributed, large-scale distributed deep learning with multiple GPUs with either TensorFlow, Keras, PyTorch, or MXNet. Let's go back and check on our PyTorch. Okay, it's done. So now if we were to activate the environment, then we should be able to do Python and then import torch. Yep. So we can exit. And just because I think we should have this. Ooh, but did we install ipykernel? Let's find out if ipykernel was installed. If not, we'll install it. PyTorch environment. So basically, I'm going to try to quickly create a custom kernel for PyTorch environment. No module named ipykernel. So this is the error that you would get if you didn't have the ipykernel module or package installed. So let's do Conda Install ipykernel. And then I'll go back here before I forget and add ipykernel to my environment file, and I'll save that. And taking a little bit longer than expected. So at this point, why don't I open up the discussion for questions, or the floor for questions. So any questions about anything that we've covered today? And I'll let this run until it's done. You know, you can ask questions about anything we've covered today. Anything that you might like. You know, if you're interested in using Conda, you know, in your own work, but aren't really sure or have questions about that, you know, you can ask questions about that too. Here we go. So it looks like it found everything that it needs. Okay, so now it's installed. So now I should be able to run this command again. And it's done. So I created the custom Jupyter kernel. And now just refresh this a few times. Wait a little bit. Eventually it will materialize. Try to close the launcher. There we go, finally. And again, so we could open a notebook and then we could do import torch. And there we go. Okay. I'll just close that. Discard and delete. Okay, so I gather that no one has any questions.
Hello?
Yes.
So if I understood correctly, Conda will manage things that I do through Conda. But
Yes.
if I install, like, let's say something else, that will not be kept track of, yeah?
That's correct. Yes. So only things that are installed via Conda will Conda basically have any awareness of or keep track of. There are some kind of minor caveats to that, like the NVCC meta package that I mentioned here. Basically, you've installed a system version of NVIDIA's CUDA toolkit, and then this package basically tricks your Conda environment to be aware of the existing CUDA toolkit that is installed on the system. There are a few other examples of packages that trick your Conda environment to be aware of stuff that's been installed elsewhere, but in general, Conda will not be aware of software that you've installed via some other way.
Okay. So basically now, as long as I keep using Conda, I can take that YAML file and go somewhere else and start all over again if I need to do that.
Correct.
Okay.
Any other questions?
Now, just in the page you were showing now, there is something was using Node.js.
Yes.
And Node.js has its own package manager. So are these also kept track of, or?
Right. So what? Okay. So specifically, what was being used there was, so Jupyter Lab itself is a Node Node.js application. So the front end that you see, like when you're interacting in the browser, is basically a Node.js application. And so when users or in the community kind of create extensions to Jupyter Lab to do different things, they're distributed as Node packages. So if you want to, at the moment, if you want to install Jupyter Lab extensions, then you need to have a version of Node installed in your Conda environment so that Node can be used to fetch these packages that are available and distributed via Node's package manager and make sure they get installed in the right place so that they can be found properly within the Conda environment. It's a bit of so that's basically why Node is there. It's only for installing extensions to Jupyter Lab. In the future, Jupyter Lab is making it so that you actually don't need to have Node available, and it will handle this in some other way. But what basically, I guess to answer your question, is that when you install Node in your Conda environment, Node will use the Node in your Conda environment that you've installed will use its own package manager to fetch things just like it would if you were using Node.js, and NPM, I think, is the package manager for Node.
Okay. Okay.
It's a good example of Conda and like multi-programming language environments. So a lot of the Python, not just like the tools like Jupyter Lab and Jupyter Notebooks that are using a lot of JavaScript because they're browser-based tools, a lot of data visualization packages in Python are Python wrappers around JavaScript kind of plotting libraries that take advantage of all of the browser interactivity features that you get when you work with JavaScript. Any other questions? Okay. Well, thank you guys very much for spending the afternoon with me. I always enjoy teaching this course because Conda has been one of the tools that has really both made me a better data scientist, machine learning engineer, computational scientist, however you want to kind of label yourself. The ability to manage your own software stack yourself and install whatever you need when you need it is really liberating. And Conda has really expanded, the work that I can do, and it made me a lot more productive. And a whole host of problems that I used to have when I was getting started in this field, I don't have anymore because I use Conda effectively. And so I really like teaching this to users here at Calst and wherever, because I feel like it's a very empowering tool to learn how to use. So thank you very much for spending the afternoon with me again. And this recording should be up on YouTube probably tomorrow. I probably won't get around to putting it up this evening, but it should be up sometime tomorrow. And also I'll be sending out via email a feedback form to get some feedback from you to see how we might improve this workshop in the future. So thank you very much. And thank you for your interest in data science training with the Calst Visualization Core Lab. Bye.